this video, I'll be going over my solution to the third Project Euler problem from my practice streams. The third problem involves doing factorization of large integers into prime factors, and therefore it'll involve looking at the sieve algorithm and generating a list of primes and doing divisibility tests. Let's get into it. The prime factors of 13,195 are 5, 7, 13, and 29. What is the largest prime factor of the number, well, this number? So the thing with a factorization problem is I know that it's sort of a theoretically hard thing to factorize large numbers. Now, this isn't a particularly large number, so I might have not needed to go as far as I did, and it turned out I was kind of overshooting with my first idea, but my first idea was to build a factorization table. And my idea for what a factorization table would be is just a table of a bunch of numbers that I compute in one go that contains a single prime factor for every element in the table. So if this is the example, like a sketch of the first 10 elements of the factorization table, then you can see like the first few numbers are all directly, they have their own value in that slot, but 4 maps to a 2 because 4 isn't prime, but 2 is a prime factor that divides 4. 6 maps to 2, 9 maps to 3, and so on, right? So each slot has a prime factor in it that divides the index into that slot, if that makes sense. This way I could take any number and go, how do I get a prime factor for this thing? And the table would provide an answer. Now, spoiler warning, I can't actually solve this problem using this idea. Later on, I will figure out, as we're going along here, you'll see me figure out that idea was just not going to work. I just hadn't thought yet through the details of why that wasn't going to work, and I'm taking you through the process I actually went through on stream to explore the problem. So from here, the next thing I looked at was how I would go about implementing the factorization table, and by implemented it, what I really mean is the routine that fills the table in the first place. And the idea I had was to basically modify the idea of a prime sieve. So a prime sieve is an algorithm for generating a list of primes, and it starts with a table that's just the list of all the numbers, or in reality, we're not going to actually store a list of numbers in the data, but for conceptual reasons, it's easy to think of the algorithm by looking at it as a list of all the numbers. And then you start marking things off that list as you're building up the prime. So first of all, we're going to mark off the number 1 because it's not a prime. And then the sieve can actually begin. So the way the sieve works is we look at the next number that we haven't marked off, and that's the next prime. So 2 is the first prime we find this way, and then we mark off all the multiples of 2. So we could take the 2 we just got and we step by 2 forward, and we mark off 4, 6, 8, and so on until we've marked off all the multiples of 2 up to the end of our table. And then we look and see what's the next number that's not marked off, and the answer is 3. So that goes onto our list of primes, and we mark off all the multiples of 3. So we just step forward from 3 by 3. We were sort of incrementing through the table by 3s now, marking things off. Then the next thing we find that isn't marked is 5, because 4 is the next number, but that got marked off earlier. So now 5 goes onto the list of primes, and we mark off all the 5s. And so what this is effectively doing as it's going is it's eliminating all the numbers that must be composite by saying, hey, we already found a way to divide into this, and the way we know we found a way to divide into it is that the only time we mark something off is when it's a multiple of a smaller number, right? So like, for instance, 4 got marked off because it's a multiple of 2, and all the multiples of 2 got marked off when we put 2 on our list of primes. Similarly, 9 is a multiple of 3, and so it got marked off when we hit 3 for the first time, and so all the things that were multiples of 3 were discovered and marked. Anything we don't mark before we reach it must not have any divisors smaller than itself, or it would have been marked. So those are our primes. That's the whole idea of a prime sieve. Now, there are 2 easy ideas to add to this algorithm to optimize it a little bit. The first is to take advantage of the fact that it's pretty easy to check for divisibility by 2. If you have an even number, that's an easy thing to figure out, where it's a little bit more expensive to do most division work on a computer. Division by 2 and divisibility tests by 2 are pretty easy. So we can take advantage of that to cut the entire table that we have to stride through in half by just skipping all of the even slots and only representing odd numbers in the table. And then we the trade-off to that reduction of the size of the table is that we have to do a slight special case path for handling division by 2 when we go to use the table. And then the other optimization we can apply is that we can actually start the stride much farther ahead than just the next multiple of the prime. So for example, if we have the prime 17, the next multiple of 17 is 34, but we don't actually have to start the stride from there because it turns out 34 will already be marked. Well, 34 won't even be in the table because it's even. But if you go to the next multiple, 3 times 17, that'll also be marked because 3's have already been marked, and 5 times 17 will already be marked, and 7 times 17 will already be marked. So you don't have to start marking things off the table until 17 times 17. That's the first possible number bigger than 17 that's a multiple of 17 and isn't already marked. So those two optimizations make this just a little bit tighter and a little faster. So we'll be using those whenever we implement this too. So my idea for a factorization table was to use that same idea of a sieve where you take a number that you know is prime and you mark it off in a table, except instead of just marking things off in a table, I would actually store into the table what multiple I found, what prime factor I found for that slot. So for instance, when you find 3 and you're not just marking off all those slots, but you're putting 3 in all those slots. So you now know where all the multiples of 3 are in your table. And then all the rest of the empty slots are things that need other primes because they aren't divisible by 3, right? And then you fill in other things with 5 and 7 and so on until you found all the primes and you've marked off every single number in the table with one of its prime divisors. That was the idea of the factorization table. But as I alluded to earlier, the factorization table is just not going to work, and this is where I discovered that. And I discovered it when I went to see the size of the number we were actually going to be trying to factor. And the reason that matters is because when we go to factor that number, we have to include that number in our table for it to actually help us at all. If the number we're trying to factor isn't reached by our factorization table's sort of upper bound, then it doesn't tell us anything about how to factor that number. And the number we need to factor is this like large 64-bit size, like you can't represent it in 32 bits thing here on the screen here. And so I'm not going to build a table with like that many slots and have 64-bit integers in each slot. It's way more than what I had appreciated. So I ended up scrapping that idea and coming up with a new one. So what I'm going to do instead is just run the prime sieve to generate a list of primes and then do a divisibility test against all of those primes, or using all of those primes against the large X number that we're trying to factorize. And I do think I still ended up overcomplicating this a little bit by trying not to let the prime list get too large. And the trick I was using there is that you really only have to divide by numbers no larger than the square root of X, because it turns out that if X is not prime, then one of its factors is less than or equal to the square root of X. So we'll either find a divisor or we'll find out that X is its own largest prime divisor, right? And then the other trick is that if you define a divisor, the thing you have left over, for instance, if you discover it's divisible by 3, then the other prime might be larger than the square root of X. So it's a little bit complicated. You have to test if the thing you have left over is divisible still. So it's a little bit hard to be sure when to stop. And like I said, this might have just overcomplicated things. Probably what I should have done in retrospect is to just build a list of numbers up to the square root of X, find the largest one that divides that, and then test if that was a correct answer in a sort of more direct way, and then only doing this extra work if it confirmed that that wasn't a correct answer. And I could have tested if that was a correct answer by looking at the X divided by the prime I find and factorizing that separately. But that was, just my head was trying to build the full solution that would give me an answer in one run, rather than a useful tool that I could apply several times to keep the code simple. So I ended up kind of hacking around and making this slightly complicated algorithm that does solve the problem eventually. But I don't really think it's worth explaining the algorithm. It's just not that interesting of an algorithm. It's not a very good one, in my opinion. So I'm just going to let this run ahead and we'll get to the programming. So this is the first problem that actually involved some interesting memory management stuff. I needed a couple of buffers, one for the list of primes and one for the table that has all the marks for the sieve. And I decided to do the memory management using the arenas that I already have and doing it all in C++ rather than doing some separate memory management sort of system in assembly, which would have taken a while to conceive of and build. And instead of trying to call for the arenas that I already have from assembly, I just said, you know what, I'm going to do a little bit of hybrid work on this one. I'm going to do the C++ part to grab the memory, and then I will switch to assembly when all the memory management is done. So whatever compute work that needs to be done once buffers are established, that's still being solved in the assembly part. But I'm not so interested in like practicing doing bookkeeping of memory management in assembly, because I just don't think there's a lot to learn there in terms of the instruction set, and it would more just be a lot of assembly typing for no reason. That's exactly what a higher level language helps with, is those kinds of higher level things being automated. But I do want to go and learn sort of the details of once the high level stuff that doesn't need to be necessarily carefully generated is done. I want to hand generate the parts that are more interesting in doing like the core compute work of the problem. So that's why it's set up this way, and what makes it a little bit easier than if I had done the memory management in a more complex way. It probably would have taken a lot longer to solve this problem. So I think this was a good way to go about it. Another interesting topic that comes up in this problem is how to do divisibility tests. So if you're not familiar with assembly and how the instructions for division work, it might seem like this is something that's going to be more tedious than if you were in C, because I know when I was a new C programmer, I didn't really appreciate how division was working at a low level. And actually, I would think of something like doing division as quite an easy thing to do, but doing a divisibility test would be kind of daunting, because how I would probably go about doing that is I would think, well, a division is successful if you can divide perfectly, and the way I would test if I divide perfectly is to see if any rounding happened. And so maybe the way I would figure out if rounding happened is I would do a division and then multiply the denominator back in and see if you get back the exact same result. And then maybe I'd get a little more advanced and think, no, I should use a modulo, and when I do the modulo, I'll find out if it's a perfect division by looking at a remainder, and a remainder of 0 indicates that something divides perfectly, and other remainders indicate that they don't divide perfectly. But then I'd get confused by the fact that I sometimes would find I want to do a division and a modulo, and they look like two discrete operations, but one of them can actually sort of be simplified from the other one. So if you've already done a modulo, or if you've already done a divide, it seems like that should make the other one easier, but then they're two discrete things that share some amount of logic but are slightly different from each other. And it turns out that all of that was worrying about pretty much nothing, because at the assembly level, there's just one div instruction that does the whole job. It gives you a quotient, so the result of dividing two numbers, and a remainder in one go. And so all of that high level abstraction that C gives you actually obscured away the fact that this is a relatively easy thing to do, and it feels easier in assembly, at least to me. So I wanted to just go over real quick how this instruction works, because I think stuff like this, where the actual way it works in assembly somehow feels simpler than the higher level stuff, I think that's so fascinating. So I'm going to go over this one real quick. So the way this instruction works is you put in two inputs. There's a numerator and a denominator. They each are a register sized value, but the numerator is always in the A register. So for instance, in the RAX register, which is the 8-byte version of the A register. And then the denominator is specified as any register you want. So you get to say like, oh, I'm using this register for the denominator or that one. So you have two inputs. One of them is a fixed register and the other one is whichever register you want it to be. And then the results go into two fixed registers as well, with the quotient going into RAX and the remainder going into RDX. And one other thing that goes on here that I skipped over is that actually the numerator is composed of two parts. So RAX and RDX are both numerators, and the RDX is the high bit. So usually we have to clear those to 0 first in order to do a division. IDiv stands for assigned division, so sometimes we also have to clear it to ones for negative numbers. But either way, the RDX registers are high bits and the RAX is our low bits. So we have actually two registers of numerator bits and one register of denominator bits. So putting this together, to do a divisibility test, I take the numerator I want to test and put it into RAX. I clear out RDX to 0, assuming that I'm doing unsigned integer for division here. I put my divisor into any other register, and I can specify that register into the instruction. And then once I do the instruction, I test RDX, and an RDX value of 0 indicates clean division. Anything else indicates that it did not divide cleanly, and that's how I can do divisibility tests in this problem and in future problems.